All right, let's talk about something you've probably seen 100 times in math class. Two simple vertical bars. But behind them is a really powerful idea, one that goes way beyond just making a number positive. Yep, we're talking about absolute value. Yeah, you've seen these things, right? The absolute value of x. You probably learned it as a simple rule, just make the number positive. But what's really going on here? What do they actually mean? So, is it just about ditching the minus sign? Well, it kind of seems that way on the surface, but there's a much bigger, much more powerful concept at play. And that concept unlocks a whole lot more than just flipping signs. Okay, let's really dive into this. Here's the first big mind shift you need to make. The most important thing is to stop thinking about plus or minus signs and start thinking about distance. And that's it. That's the key. Geometrically, the absolute value is just a measurement. It tells you how many steps, how many units a number is away from zero. It doesn't care if you went left or right to get there. Exactly. It's all about how far, not which way. And because distance is always a positive thing, or zero, the absolute value of a number can never, ever be negative. You can't have negative distance. So you can look at this in two ways, and they're really just two sides of the same coin. On the left, you've got the intuitive visual idea. It's just a distance on a line. And on the right, that's the formal algebra that makes it all work. If a number's already positive, well, its distance is just itself. But if it's negative, its distance is its opposite, which, you guessed it, flips it to be positive. Okay, so that's the theory, but how does this whole distance idea actually help us solve problems? Well, let's see how it builds into a really powerful method for solving equations. To solve these things, you have to isolate the absolute value part first. I absolutely love this onion analogy from our sources because it's perfect. You have to peel back all the outside layers of arithmetic, one by one, to get to the core of the problem. So let's just walk through this one. We start with our equation. First, we gotta undo that subtraction. So we add 10 to both sides. That's layer 1. Gone. Then we undo the multiplication by dividing by 2. Boom, layer 2 is gone. And now the absolute value is all by itself. Okay, and now that it's isolated, we can finally use our core idea. We know that the stuff inside those bars, the 3x minus 6, has to be exactly 3 units away from 0. And how can that happen? Well, there are two ways. It could be sitting at positive 3, or it could be sitting at negative 3. So we solve both of those simple, separate equations, and we get our two possible values for x. This is perfect because it shows the whole idea in action. Two totally different points on the number line can have the exact same distance from 0. So this two-case logic is super powerful, right? But you gotta be careful. It also reveals some common traps and a few special rules, especially when we start talking about inequalities. But hang on a second. What if a problem asks you to find a value whose distance is negative? Like, what if you do all that work to isolate the absolute value and you end up with it being equal to negative 6? Yep, no solution at all. It's a trick question. It's impossible. So here's the crucial takeaway. If you ever isolate an absolute value and see that it equals a negative number, you can just stop. Stop right there. Because distance can't be negative. There is no value of x in the universe that could make that equation true. Now, with inequalities, things get even more interesting. It's still about splitting it into two cases, but how you split it really matters. If the absolute value is less than a number, it means the distance is small. It's trapped in a single range between the positive and negative value. But if it's greater than a number, it means the distance is large, so the solution breaks apart into two separate pieces shooting off in opposite directions. And what's so cool about this fundamental idea of distance is that it doesn't just live on a simple one-dimensional number line. It scales up beautifully. Take complex numbers, for example. They have a real part and an imaginary part. Well, their absolute value, which has the fancy name modulus, is just the straight line distance from that point back to the origin on the 2D plane. You even use the Pythagorean theorem to find it. It's literally the hypotenuse of a triangle. So you see, it all comes back to the same unifying idea. Doesn't matter if it's a simple number on a line or a complex number on a plane. The job of the absolute value is always the same. Measure the distance from home base, from the origin. Okay, I know this can all feel a little abstract, a little math class, but this idea of an acceptable range or a deviation from some target, it is everywhere in the real world. I mean, seriously, think about it. Error margins in scientific measurements, the tiny tolerances needed in manufacturing, the accuracy of your GPS, stock market fluctuations, even medical dosages. Absolute value is the language we use to talk about what's close enough, what's an acceptable error. The GPS example is just perfect for this. Your phone doesn't know exactly where you are, it gives you a circle of probability, a range. That's literally an absolute value inequality in action. It's telling you the maximum distance between where it thinks you are and where you actually are. So, what's the big takeaway from all this? It's that those two little vertical bars are about so much more than making a number positive. They're a powerful way to talk about distance. The next time you see them, don't just think, flip the sign. Think, how far from zero? And when you do that, you'll start to see how this one simple, powerful idea has the ability to describe everything from a number line to the complex and sometimes messy world all around us.